Very warm welcome to this hybrid webinar on sustainable textile. My name is Pekka Orpana and I'm the ambassador of Finland in Japan. During the webinar, we will see presentations and discuss how we in Finland and in Japan can together create smart textiles from forests and how we can create solutions for perfect circular loops for the life cycle of textiles. Climate change and bio and circular economies go hand in hand. In order to mitigate climate change, we have to move from fossil-based economy to bio-based one and use the existing materials wisely and reuse them as much as we can. Today, textiles have turned out to be an environmental problem, consuming the resources we would need for food production, and oil-based textiles are polluting our lands and oceans. As the need for textiles is constantly increasing, research institutes and companies have the responsibility to find solutions to these environmental challenges and ways to meet the growing customer demand for sustainable textiles. In Finland and in Japan, we have answered to this call. We have a long tradition of cooperation between companies and in research activities in forest, bioeconomy, and bio-based products. An excellent example is the cooperation between Japanese Itochu and Finnish Metsä Group on a joint venture plant on cellulose fibers. Koura, the new textile fiber brand developed in these cooperations, was launched this spring in Japan Fashion Week. Finland and Japan are both countries of forests, which affects profoundly our cultures and our respect to nature, environment, and sustainability. Finland has the most advanced forest industries in the world in full swing to play a key role in the transition to bio and circular economies. Our strength is a very strong sustainable forest management we established already over 100 years ago when we carried out the first national forest inventory. These national forest inventories have been carried out regularly in 5 to 10 year cycles. Together with Japan, we have a lot of complementary knowledge, know-how, and industrial and commercial value chains in using forests, wood, and creating sustainable textiles. Today you will hear insights from Japanese and Finnish companies, institutes and research communities about sustainable forestry, data management, circular solutions, and about novel wood-based textile fibers ready to conquer the world markets. I hope you will find the presentations and discussions interesting and useful, and that they will give you information, ideas and connections for further cooperation and ultimately to good and sustainable business opportunities. Thank you very much.
オルパナ大使ありがとうございました。続いてご登場いただくのは、ビジネスフィンランドバイオサーキュラーエコノミー担当
Konnichiwa, ladies and gentlemen. Hope you and your families are all well in these special times. I am Helvi Väisänen, Senior Advisor at Business Finland. I'm here to tell you about Finland as business environment and encourage you to kickstart your bio-based business in Finland. Our message is simple and clear. Let's get in line with sustainable development. Let's get rid of fossil resources. Let's find a way to generate more wealth, well-being, and growth from natural resources. The environmental urgency is stronger than ever. The key drivers are the consumers, the smart investors, and the rapidly changing regulation. A whole new generation is coming, and they are not going to accept the way our generation has worked if we do not change. Finland is in the leading position in the bio-based solutions. This is why we can help the rest of the world also to embark on this journey. Business Finland is the government organization for innovation funding, trade, travel and investment promotion. We are headquartered in Helsinki, employ 600 experts in 40 offices globally and in 20 regional offices in Finland. So, why work with Finland? When you are looking for an ideal partner, what are you looking for? Well, let me guess. I think if you are a large company, I think you are looking for a business environment with stability, predictability, and high level of safety. Perhaps university-industry collaboration in research is of importance to you. And last but not least, I think you are looking for partners that you can trust on, people that do what they promise. And look at this. This is Finland. According to independent studies such as the World Economic Forum, Global Innovation Index, Bloomberg Innovation Index, Finland ranks the best business environment in the world. Number 1 in primary education, the best in the world of innovation, number 1 in university industry research collaboration in the world, the best destination in EU for international business expansion, the most stable country in the world, and for the 4th year in a row, we are the happiest country in the world. We may sit in the darkness for a couple of months in the year, but everything works in this society. People have great work-life balance, and this is why Finland makes so much sense. We offer business opportunities in high-tech and services, in bio and circular economy, clean tech, health, ICT and digitalization, travel and tourism. Finland has lived for 400 years from the forests, so there is a long, long history. And we believe we will be living from the forests for the next hundreds of years for 2 reasons. Number 1, everything that is made out of oil today can be made of wood tomorrow, and in Finland we are already doing it. Number 2, we offer a unique platform for bio-based growth. The industry cluster is strong and it's renewing. There is growth and partnering potential, governmental facilitation, abundant feedstock, and world-class competence. You can say that we have the heads and the woods to make it happen. Finland is the base for international bioproduct manufacturers. You can see from the collection of these logos that most of the big international integrators are here in Finland. From Japanese companies, Nippon Paper and Misaba are based in Finland, but the flagship of Finnish-Japanese collaboration is the partnership between Itochu Corporation and Metsä Group. That goes back decades. Marubeni Corporation has re-established their presence in Finland last year, opening the Northern European office in Helsinki. We look forward to a fruitful win-win collaboration with Marubeni Corporation. And please note, there is room for more companies in our ecosystem. Finland is the epicenter of bio-based growth. This picture illustrates that we have a pipeline of new advanced sustainable products in development in Finland. On the left-hand side, you can see the new advanced products already in commercial production, such as the 100% renewable diesel, the microfibrillated cellulose, pyrolysis oil, high-quality barrier board, cross-laminated timber, and craft lignin. In the center, you can see the new product developments close to commercialization, such as the wood-based textiles, the next-generation bio-based packaging, the biocomposites, lignin applications, the bio-based chemicals. And on the right-hand side, you see our new open innovation ecosystems, such as Expand Fiber, Click Innovation, Telaketju, which is the co-innovation of circular economy textiles, and Seed, the digital transformation of bio-based industry, and Finseres. These are high potential ecosystems. They are in development and looking for international partners. Our success is based on a deep understanding of the entire bioproduct value chain, world-class experimental research, integration of cross-disciplinary sciences, and open access pilots and demonstration platforms. So if you are a large company seeking growth and sustainable competitiveness for your company's future, please contact us. We at Invest in Finland are your partner, helping you in opportunity analysis, exploring entry alternatives, data collection and analysis. We facilitate corporate networking with right partners and help you in setting up your business. Our comprehensive services are confidential and complementary. So this is my contact information. We would love to hear from you and set up a time to discuss your goals, understand your challenges, and help you to kickstart your bio-based business in Finland. Ladies and gentlemen, thank you very much for your attention. Arigatou gozaimasu.
化石由来の原料に代わるエネルギーとして様々な分野での活用が期待されている木質バイオマス。その普及のためには真に持続可能な森林管理が必要です。フィンランドは日本と同様世界でも有数の森林国です。国土の 80% を占める森林は生活を支える貴重な資源として人々を貧困から救ってきました。
200 years ago, this was not the case. Finland was one of the poorest countries in Europe, and our forests were overexploited, almost raped, by slash and burn agriculture and poorly done forest management.
フィンランド語でレイプを意味するライスカウスは、かつて森林破壊を意味する言葉でした。フィンランドではかつて度重なる焼き畑工作によって国土の広い範囲が不毛の地となりました。しかし19世紀になって大きな変化が起こります。製材所や製紙業の発展により森林は前にも増して大きな経済的価値を持つようになったのです。当時のフィンランドの農家は自分たちの土地にある森林の潜在的な価値に気づきました。やがて持続可能な森林管理の文化が構築されていきます。木を切ったら新しい木を植えるというシンプルなルールが当たり前になったのです。
A bit over 100 years, our forests has been managed intensively. A lot of R&D, well-organized forest professionals, and hundreds of thousands of private forest owners have created together this remarkable renewable resource, offering all kind of ecosystem services for all of us. This tree is not growing now. It will wait few months more, and then it will start to grow together with 30 billion other trees in Finland. Together they will produce 1 million cubic meters of new biomass every day. And at the end of the growing season, we will have 110 million cubic meters of new wood in our forests. We harvest every year only 60% of our annual growth. That means that our forest resources increase with about 20 million cubic meters every year. And that 60% of harvest is crucial for this country. It offered last year 66,000 jobs, 4% of our GNP, and 19% of our exports.
People see it as something, if I plant a tree, my grandchildren are going to be the one that actually reap the benefits. But it's seen as a sort of a way of sort of providing for people, and that also gives the motivation to keep it in as good shape as possible.
Finnish forests are a remarkable carbon sink. The annual net sink is about 30 million CO2 equivalent tons. It is about 50% of all CO2 emissions in Finland. But that is not the case in all countries. Because of forest management and especially because of forest fires, forests can be remarkable source of CO2 instead of being effective sink.
フィンランドでは世界に先駆けた調査方式で森林バイオマスの炭素吸収量を算出しています。
Forest data is really important when running sustainable forestry. Finnish national forest inventory is 100 years old. During that time, we have been able to get huge amount of exact data from our forests, and that has been helping us so that we are utilizing the opportunities of forests, but not over-exploiting our resources. Satellite imagery we have been using already for decades. Nowadays we are using also LiDAR, photogrammetry, and all kind of sensors to get more reliable information and data about forests.
Metsästä mitataan puukoealoja, eli siellä käydään mittaamassa niin kuin pienten muutaman 100 neliömetrin tai muutaman 1000 neliömetrin alueiden puusto melko huolella. Minkälaisia puita, kuinka paljon, minkä kokoisia, mitä puulajia siellä esiintyy. Tämän aineiston avulla tyypillisesti tarvitaan, sanotaan muutama 100 tämmöistä koealaa, niin me voidaan rakentaa siihen laserkeilauksen tuottamaan pistepilveen tilastollinen malli, joka sanoo, että jos tuommoinen pistepilvi siellä esiintyy, niin silloin näistä koealoista voimme päätellä, että melko varmasti siellä on tämmöinen puusto alla. Ja tällä tavalla tosiaan saadaan sitten laskettua puustoennusteet kaikkialle, minne se laserkeila on ulottunut.
森林管理を効率的に行うためには、デジタル化された森林データが不可欠です。アルボナウト社は森林調査サービスの提供と森林資源管理開発の情報システムに特化した世界でも有数の企業です。御社で開発されている森林情報システムについて教えてください。
私たちの森林情報システムは森林生態系の最新で正確なデジタル情報を提供し、その情報は森林に関わるすべての組織で意思決定に用いることができます。ユーザーの活動が環境保全、経済性、社会性のどれを志向していても、システムは目的に応じて森林資源を最も有効に活用するのに必要な情報を提供します。最新のテクノロジーや方法で森林資源量の特定や位置情報の特定を行います。ユーザーはシステム画面で山林協会や林分協会などの空間管理データを閲覧、編集、そして保存することができます。こうした情報はクラウド上で共有され、オフィスのパソコンからでも、作業現場のモバイル機器からでもアクセスが可能です。
非常に高度なシステムなんですね。実際に使っているところを見せていただけますか？
はい、もちろんです。このようにモバイル端末の画面上に意思決定をサポートする情報レイヤーが表示されます。私たちは取得したセンサーデータを分析することから始め、様々なデータを組み合わせることで独自のデータを作り出します。完成したデータがこのように空間情報としてはっきり可視化されることで、森林管理者が効率的に作業計画を立てるのに役立ちます。例えば、ユーザーが材木の伐採計画を立てるとします。システム上ではすでに伐採可能な森林資源が詳細に割り出され、位置情報とともに示されています。森林事業者は険しい地形を避けるようにして、材木の運搬ルートや保管場所をマッピングし、輸送計画を立てます。そして、これらすべての情報は、伐採に関わるすべての事業者にデジタルフォーマットで伝えられることができ、同じプラットフォーム上でスムーズなやり取りを行うことが可能です。
フィンランドは先進的な高性能林業機械の製造に注力している会社がたくさんあります。1970年にエイナリ・ビドグレンによって設立されたポンセ社。効率的で持続可能な CTL 方式の先駆者です。 これまでに1万5000台以上の林業機械を製造した実績があります。この CTL 方式とは一体何なのでしょうか。CTL はカットゥーレングスの略で、木材を林内でそれぞれの用途に応じて増材する単管集材方式を指しています。現在、機械で伐採された世界の木材のうちの実に3分の2が、この CTL 方式を採用しています。近年、急速に導入が増加している CTL 方式。その CTL 方式に不可欠なのは、効率的で高い適応性を持ち、環境に優しく、ユーザーに優れた快適さを提供する CTL 林業機械です。では、作業工程を見ていきましょう。CTL 方式では、ハーベスタとフォアタという2台の林業機械を使って行われます。まずはじめにハーベスタが木を伐採し、枝払い、計測して、注文に応じた採材を行い丸太にしていきます。次に、林内に積まれた丸太をフォワードで沿道へ輸送します。その後、丸太材は製材所へ、パルプ材はパルプ工場へと、それぞれの目的地へ輸送されます。CTL ハーベスタの自動化システムは、生産量を最大化し、廃棄を最小限に抑えます。多様な機能を持つ CTL ハーベスタは、困難な条件の現場でも安定した性能を発揮し、天候、地形に関係なく、あらゆる条件下での作業に適しています。フィンランドよりもはるかに厳しい条件の日本の山林においても効率的であることが実証されています。高品質の森林管理を可能にする CTL 方式。ポンセ社は CTL 方式の林業機械と情報システムに特化した企業として重要な役割を果たしています。ケスラ社は1960年創業の長い歴史を持つフィンランド有数の林業機械メーカーです。世界35カ国以上の国々に高品質でユーザーフレンドリーな製品を提供しています。2005年に日本市場に参入して以来、日本の環境に適応した林業用機械へのアタッチメントを開発提供し、日本林業の機械化に貢献しています。ケスラ製品の最大の特徴は、様々なベースマシンに装着できるという汎用性です。
Since the very beginning, we have listened for the specific needs from our long-term partners in Japan. Also often, the harvesting conditions in Japan are challenging with planted steep mountain forests and poor bearing capacity of terrain, for example. This is why the forwarding trails must be constructed firmly, and you cannot use very heavy machines. However, our unique Kesla stroke harvester can handle big trees with big branches, and it can be used with lightweight base machine, making the work possible on steep mountains on those conditions. We have been also equipping special local tracked forwarders with our Kesla timber loader to make the work more productive to load, transport the logs downhill, the narrow and steep trails, and also to unload to the roadside. In addition, during the years, we have supplied to Japan Kesla's energy-efficient roller harvesters for less steep conditions, different kind of conditions in Japanese forests, timber cranes for local timber trucks, and mobile chippers for bioenergy production from wood.
ケスラの製品は日本の林業の機械化に貢献されているんですね。日本の厳しい環境に適したソリューションも素晴らしいと思いました。日本の林業は今後ますます機械化の方向に向かいますが、日本市場に向けた取り組みについて教えてください。
Yes, since 2005 we have got a big growing number of wonderful Kesla machine owners all around Japan, who we frequently visit on the field and see on annual forestry exhibition. It's really like a Kesla family in Japan. Even our very first stroke harvester was still in use when we courteously visited the owner in the forest some time ago. The simulator is good help, for example, for the forestry schools to educate new operators. We have also new cloud-based wireless logging data transfer system and remote service applications, to mention. Our solutions already give a great possibility for optimizing the machines for exact specific need of different kind of Japanese forest ecologically and profitably. The future holds new smarter forestry innovations to operate sustainably in Japan's beautiful forest.
バイオマスを大規模に利用するためには、適切な森林管理ができていることが大前提なのですが、もう一つ重要なことは、この貴重な原料である木材を無駄なく効率的に利用することです。つまり、製造工程の最適化や、製品の価値や寿命を最大限に生かしていくことが求められています。
Sustainable is something that can actually, it's not depleted over time. That's basically what it is. So we'll be able to maintain or even increase that supply. So rather than making things poorer, we should be actually be able to replenish. And I think from my sort of perspective, that is the definition of sustainable. So we can pass it on to the next generation that just keeps on giving and giving more than it gave before. I think what we need to do really is to start thinking more about the sort of the biomass as a sort of a not an abundant resource, but a limited resource. And what does it actually mean then? We have the targets of reducing fossil carbon in our materials. So what we need to start doing is that what is the most effective way of doing that? And then we are basically looking at two things. First of all, we need to start thinking about the tree as a tree. So making sure that we use every part of it as much as we can in order to maximize the amount of biogenic carbon that one can use to sort of reduce the fossil carbon in products. The second thing is looking at the circularity. So how can we make sure that the carbon stays in the products longer? Of course, there are a lot of products which are sort of disposable and that's it. But there are also a lot of opportunities for sort of introducing also circular economy more into the bioeconomy. And then, of course, when the aim is to reduce the amount of fossil carbon, then we also have to start thinking that whenever we still need to replenish the carbon from somewhere. So where do we take the virgin carbon? Do we take it from the renewable sources or do we take it from the fossil sources?
化石由来の原料から再生可能な原料へ移行する鍵は、北方森林国が強く連携することです。
We can do much more if we are able to globally be networked in a best possible fashion. And I think that this joint effort, putting up the Boreal Alliance, it's only the beginning, and we hope that we will expand and that we can really make large impact.
世界的なパンデミックによって新しいバイオベース素材開発への期待が高まっています。
A lot of the personal protective equipment, or PPE, is being made out of petroleum products. So surgical masks, N95 masks, are made predominantly from polyethylene, polypropylene. Very nice chemicals, they're very chemically resistant, but that also makes them not biodegradable. Although they're only used on your body for minutes to hours, they will, when put on the ground, last hundreds, if not thousands of years. So we have some interesting opportunities to take bioproducts, use them in the medical industry, not just inside the body, but also outside the body to solve these problems, to help us create materials that are more environmentally friendly.
代替品としてのバイオベース製品は、環境問題を解決するというだけではありません。必要な微生物だけを狙って攻撃することができるという特性を利用した新たな役割が注目されています。植物にはポリフェノール成分などの有用な二次代謝産物があり、病原体に対抗するなど多くの機能を持っています。
Because the trees need these compounds also for their own defense. So they need to fight against different pathogens, fungi, and other organisms attacking the trees. And usually these compounds are located in the bark of the tree. So it's kind of a shield against these nasty pathogens.
有効に活用されていない製材工場から発生する残廃材として木の樹皮があります。
At the moment, most of the bark is still used for energy production in the industry. So we could use it in different cascade processes to first obtain these active compounds and then use also the rest of the biomass for different purposes before it's finally burned for energy.
フィンランドの国立研究機関である自然資源研究所では、樹皮成分の新たな商用利用の創出に向けた共同研究が始まっています。
Yes, we have at the moment the project funded by Business Finland. It's this Corona Co-creation Fund, and we are collaborating with University of Jyväskylä. We have Professor Varpu Marjomäki's group in cooperation, and they are virus researchers. And together with them, we have found already very promising results of different tree extracts. And the extracts have been tested and shown activity against different virus types, including enteroviruses, which are really nasty ones to kill, also with ethanol-based disinfectants. And then we have found activity against the seasonal coronavirus and also the virus which is causing this current COVID pandemics.
自然資源研究所では最近、樹皮から付加価値を生み出す仕組みについての研究成果を発表しました。
We have studied this kind of cascade processing, where the idea is that we first, for example, extract valuable polyphenols and other water-soluble extracts out of the side stream. It can be, for example, bark. And then they are utilized for high added value products. And then the remaining biomass can be still used for other processes. So we are kind of combining different unit processes together in order to get most out of the raw material. And after the extraction process, the residues have been, for example, taken to the slow pyrolysis process. And from that process, we can get out of tar and we can get biochar and then pyrolysis liquids. And those liquids are kind of a residue which can again be directed to biogas process, AD process, and from that we can get out of biogas, for example. And the solid residues can also be directed to this AD process. By this way, we can get really most out of the raw material.
フィンランドの専門家の皆様、ありがとうございました。続きまして日本側の専門家でいらっしゃいます国立大学法人東京農工大学グローバルイノベーション研究員の船田亮教授にご登場いただきます。船田先生は日本木材学会の会長でもいらっしゃり、昨年日本農業工学会より新農林社賞を受賞されました。
Good afternoon, Japanese colleagues. I'm very happy to have a good opportunity to introduce our research activity of wood science in Japan. My name is Ryo Hibiya, the president of the Japan Wood Research Society, also the dean of the Faculty of Agriculture, Tokyo University of Agricultural Technology. I'd like to say thank you very much, Dr. Tuula, Jyske, for your invitation. Also, the Dr. Katsushi Kuroda. Thank you very much. So now we have many issues, especially the food, environment science, energy. This is the famous guideline of the SDGs. So from 1 to 17, there are many our topics. And then many things are related, closely related to the agriculture science, forest science, wood scientists. It means that to make a good solution for our future, agriculture and forest science, wood science might be very important. However, this is current achievement of SDGs. This is Japanese achievement, this is Finnish achievement. Unfortunately, we have many low score, especially 5, 12, 13, 15, 17. 13 and 15, it is related to climate change, also the environment sciences. Therefore, we have to make a good solution. Also, this is the change in temperature. So by IPCC, climate change will occur and makes the global warming. Rise in temperature, what this scenario shows that 4.8 degree increase in 2100. So also even in Japan, we have now many typhoons, many droughts, many heating. This closely related to climate changing. So we have to decrease carbon dioxide emission and also increase carbon dioxide absorption. To increase carbon dioxide absorption, we'd like to use biomass, especially with the biomass, because the biomass has huge volumes. And then this is very important of trees to reproduce renewable and carbon neutral resources with the biomass. Because photosynthesis of trees is performed by the solar energy, water, and carbon dioxide. And then therefore the radial growth, this is growth of trees, making wood, fix carbon dioxide inside. Where carbon dioxide is fixed, so this is showing the scanning electron microscope images, where if you observe xylem, so we can see that this is cell wall. But the cell wall thickness is different depending on the species. Also the climate factor affect such kind of thickness. And then main component of the cell wall exists cellulose, hemicellulose, lignin. So if we like to use biomass, we have to know that what is cellulose, what is hemicellulose, what is lignin. Also the specific gravity determines how much carbon dioxide is fixed. So determined by the cell thickness and cell morphology. Therefore, also you have to know that what kind of factor regulates such kind of thickness of cell wall, also the morphology. So I would like to show our research activity in wood science. Before talking about wood science, I would like to show overview of Japan to finish flat. So this is Japan, this is Hokkaido, this is Tokyo, Kyushu Island, and also this is Okinawa Island. You can see Japan extends from 22 degrees to 45 degrees north altitude. This means a very long country from north to south. Therefore, you can see this is Hokkaido, Sapporo, average temperature around 9 degrees. And Tokyo, 16 degrees. But in Naha, it's Okinawa Island, 23 degrees. This is also the tropical, subtropical weather. Therefore, you can see climate and the vegetation are very different depending on areas. Therefore, the species of trees also different. So this is, you can see this is number of the Japanese overview. We have many population. We have how much population density compared with Finland. But the forest rate is around 70%. Therefore, only 30% we are able to drive. And then we have used many timber. You can see here, this is Japanese timber demand, 81 million, almost cubic meter square. But we import many timber from outside. But almost 40% of Japanese timber is produced in Japan. So now this self-sufficient rate increasing. It means that we are able to use many timber now. Therefore, we have to know that how we can use wood. And then, because also we have long history of wood culture. From long time ago, we use the wooden house, wooden temple, and furniture. So this means that wood culture, we respect wood culture. Therefore, I'd like to show the purpose establishment of our society, Japan Wood Research Society. Around 65 years ago, Japan Wood Research Society was established because we'd like to use wood more around the 55 and 65 years ago. And now we have 2,000 society members. including 500 student members. So this number is quite not constant. And then, so that means that many Japanese students are interested in wood science. So, purpose. Our society promotes science, technology, related wood and other forest products like mushroom, of course, but also that we would like to promote sustainable development society by agreement and bioeconomy. But unfortunately, compared to Finland, we are probably the bioeconomy not so much developed. So for this activity, we met many purpose. This is the main activity. Most important thing of the activity, we published academic journal and scholarly books. We'd like to show one example. This year, 2020 Japan Wood Research Society Prize, Professor Yoshiki Horikawa, he investigated the cellulose. I'd like to show that one example for the activity. So, he is specialist of the wood structure, also the lignin and also hemicellulose, and also cellulose. And then he would like to now make the new wood. So I'd like to show example. So this is you can see the hierarchical structure of wood. This is very important. From trees, wood, tissue, cell wall, and then microstructure. This kind of structure determines the very good and quality of wood. Therefore, we are able to use many kinds of purpose. From wood, we are able to use for timber. From tissue, for example, pulp and paper, and then biofuel, and finally, cellulose nanofibers. So, to utilize wood high utilization, we'd like to know such kind of structure. What kind of mechanism makes such kind of hierarchical structure? Also, we'd like to keep such kind of structure. Therefore, he tried to make new wood. It means the white wood. He used also alcohol-helix bleaching. It means they removed hemicellulose lignin from wood. And then finally, he makes white wood. It means colorless block. This is a very interesting structure. For example, if we make temp-mediated oxidation, it means making the cellulose nanofiber. From such kind of white wood, we are able to make very fine structure of cellulose nanofiber. Colorless wood blocks keeps cellulose micromorphology. So therefore, he would like to say such kind of new material white wood, showing that keep such kind of hierarchical structure. Therefore, we'd like to keep this such structure. It's very important. And then we'd like to use wood for the other purpose. Finally, I'd like to show that important mission of academic society in the new era. It means that now we have quite serious problem due to COVID-19. Because our relation is collapsed by the COVID-19. So now it's quite difficult to make communication to organize a meeting or the symposium. But we have to continue to support higher education and research for the next generation. Next year, 2022, we will organize annual meeting in Nagoya and Gifu. So we are now planning that to organize annual meeting by hybrid. So new technique probably, or face-to-face combined with online. Just such kind of hybrid conference makes the good communication each other. Finally, I'd like to say thank you very much for your invitation. And so, this symposium makes more closer relations between Finland and Japan. I did Finland around 20 years ago. I enjoyed very well in Helsinki, Tampere, also the Rovaniemi. It's a very nice time. We have very good time I hope that to visit Finland again and then to make good relationship. Thank you very much for your attention. Thank you very much.
ただいまより第2部、木材由来のテキスタイル向け繊維に移らせていただきます。近年世界的に繊維の需要が増大しており、森林産業に大きなチャンスが生まれています。セルロースの新しい用途として最も注目され成長している分野はテキスタイルです。
One of the great needs globally of the textile industry is to find alternatives for cotton. Growing cotton and transforming it into textiles uses immense amounts of water, which is ecologically unsustainable. And for this, we want to find an alternative from cellulose, from the wood industry.
Well, the demand for textile fibers in general has been growing immensely during the past 50 years. And today we are producing over 100 million tons of textile fibers globally. Most of the textile fibers today are produced from oil, over half. The second largest raw material is cotton, and then about 6% is based on wood. So this is a starting point. Oil-based textile fibers are still growing. But what to do with the demand for cotton-like fibers? This is the window for the forest-based and wood-based fibers.
There is an increasing need for cellulosic fibers, no doubt. And also that for the raw material base, there is need to combine the recycling for the same. So it's not either or, but it's both. Because we need to have in a rough 10 years time, something like 50-60 million tons more textile fibers. So it's a kind of consumption explosion. And so everything is, so it's an ocean of possibilities at the moment, more than threats.
フィンランドでは現在、サステイナブルな繊維の需要の高まりに対応するために、新しい技術開発が始まっています。例えば、木材パルプから繊維を作るビスコース法は、100年以上前から使われている技術ですが、自然環境を大きく汚染するため、早急に代替技術が求められています。木材パルプの世界最大手であるフィンランドのメッツァファイバー社は昨年、アーネコスキ工場を開設し、イオン液体を使ってパルプを溶解するという前例のない方法で、セルロースを再生することに成功しました。このプロセス自体、まだ試験段階であったために、パイロット工場を建設することは大きな挑戦でした。
The development world has changed significantly during the past 20-30 years. It used to be very linear. You made your basic science, and after that phase you went into applied science, and after that phase you went into the industrial research and development. But today this all happens in parallel. So you have to be engaged in all of these levels at the same time. And when you go into your industrial research and development phase, you don't have all the answers, even the basic answers, some are open. So you have to just take higher risk, and this is all due to the globalization and the speed of things happening.
ヘルシンキ大学のイルッカ・ケレプライネン教授のチームは、イオンセル技術の鍵となるイオン液体を開発しました。アールト大学のヘーベルト・シクスタ教授によって開発されたイオンセル。現在はパイロット段階にあります。
What is new and also different to other pilot plants in the same field is that we run in a closed loop operation already at this scale. The capacity is 1.5 kilograms per hour of fibers. We have 2 lines. We have on each line 5 spinnerets. At the moment, we have close to 1 kilogram per hour capacity on each spinning line.
現在、イオンセル技術のチームは、木材由来の繊維における課題の解決に注力しています。
The high tenacity cellulose-based textile fiber compromises the elongation, and on the other hand, that is also vice versa. So To compete with synthetic textile fibers, we have to improve the mechanical properties of cellulose-based textile fiber, meaning we have to increase this tenacity and elongation simultaneously to have high toughness cellulose-based textile fiber.
カニスモリアムさんは、ノズルの形状を変えることによって優れた強振動をイオンセル繊維に持たせることが可能になると最近の論文で報告しています。
Basically, we have done the spinneret geometry change. So we found that if we have longer spinneret capillary, then fiber has, like basically cellulose solution has more time to have the alignment of the cellulose molecules. And then at the end, when we have the fibers coagulated, then the cellulose fiber has higher orientation, which results the simultaneous increase in tenacity and the elongation. So we also changed the pulp, and which is the high molecular weight pulp with very less impurities. So that also contributed to the high toughness of the iron cell fiber.
イオンセル技術におけるもう一つの優先課題は、イオン液体をリサイクルすることです。
Basically, these solvents are like any other organic solvent. They can have some degradation because of heat, because of presence of other compounds like water. They can have some reactions with these compounds.
研究の結果、溶剤のリサイクル率は着実に向上し、現在の回収率は 97% までに達しています。
And we are, of course, aiming to even increase this amount in the future to like surpass 99%. And this is something that I have done in one of my papers, that we have recycled this solvent for 5 cycles. So we recycle, and then we dissolve cellulose successfully, we spin, and then we recycle again, and so on. So 5 times. And we could clearly show that the solvent has been changed like in a very minor manner. And the cellulose that we have produced, or the regenerated cellulose, it has had like good mechanical properties. And so we could even proceed with Marimekko and produce a dress out of these produced fibers.
イオンセルの技術は他にも多くの最終製品に応用されています。
I joined Herbert's group already at the very beginning when he built up this ion cell project. I was then a postdoc, and I was responsible for installing all the equipment to get everything going. And we had a clear focus of converting wood pulp into high quality textile fibers. And it took all quite long until everything was running, but once it was working, then everything happened really fast. And rather soon we realized that these fibers are not only suitable for the textile applications, which we had in mind in the first place, but could also serve technical purposes. And so then we started to look at carbon fibers, carbonize our originally textile fibers, our cellulose-based fibers, and we found that we get actually quite high-quality carbon fibers. And more than that, this technology, the ion cell technology, allowed to also incorporate other biopolymers, polymers like lignin, who boosted the carbon content. So we could improve the carbon fibers not only from the technical point of view, but also from the economical point of view. So we increased the carbon yield.
従来の炭素繊維と生物由来の新しい炭素繊維との違いは何でしょう？
Today's carbon fibers are made from polyacrylonitrile, so PAN, that is an extremely nice material and an amazing precursor for carbon fibers. And with this precursor material, you will get the best carbon fibers that are needed in airplanes, where you really want to have the best quality because your safety is at risk there. When we have to be honest, with our bio-based carbon fibers, at least in my opinion, we will never be able to reach this extremely high quality. But that is not needed for bulk applications. So for applications like in a car, for instance, to replace certain metallic parts in car with lightweight carbon fiber composites, carbon fibers made from biomaterial would fulfill these requirements and could offer a solution there.
この分野での開発は著しく前進しています。
5 years has been like say space shuttle, so a lot of things has happened, and when we were speaking of new inventions in laboratory, now we are speaking about the things which are coming in a piloting, or they are even further. So there is capsule collection coming out. There is even certain material has come to the marketplace first time. And that's really fascinating. I believe quite a lot 5 years ago, but this has been even more rapid than I ever thought it could be.
フィンランド発のスタートアップ企業、インフィニテッドファイバー社は、セルロースカルバメートの技術を使っています。この企業もまた長い研究の道のりを歩んできました。インフィニテッドファイバー社では、廃棄物を原料にして繊維を作ることに重点を置き、すでにグローバルファッションブランドの H&M やパタゴニアなどと提携しています。
In the recycled textile, where the infinited fiber is definitely in. Just this week, a sub-branch of H&M has sold the first jeans to the open market. So that material is now commercial.
廃棄物の再資源化は EU 欧州連合のサーキュラーエコノミー戦略において重要なポイントです。繊維業界においては、バリューチェーン全体でサステイナビリティに取り組むことが前にも増して重要になってきています。
Is not only rising from the raw material. So the fiber as such is just 1/3 of the sustainability of the textile life cycle or less. So the next one, which is about the same size, is the coloring and finishing and chemical converting of the fibers when they are already textile fibers.
地球の水質汚染の原因の1/5は繊維の染色排水によるものです。染料の使用量を減らすこと、さらに洗濯のたびに染料が溶け出さないよう、繊維に永続的に付着する技術を確立することは、繊維業界や研究機関にとって重要な課題です。最近始まった EU 欧州連合のファンドによるプロジェクトグレテでは、セルロース繊維を解出してイオン液体への溶解性を最適化し、同時に染色性を向上させることを目指しています。
In Grete project, we use enzymatic modification and chemical modification in order to improve the properties of the final regenerated fiber product.
So it's not only about replacing the existing fibers or raw materials which are on the market. Grete will offer a production technology which consumes less energy and will consume less water.
With enzymes, we are capable of modifying the pulp properties so that it's more easily dissolved and form good quality dope that can be easily made into a regenerated fiber.
The functionalization used in the Grete fibers opens up new possibilities in the post-treatments of the fibers.
In Grete project, we aim to use paper-grade pulp, which requires much less processing and is more abundant, more available on the markets.
生物由来の素材には、ヒドロキシル基が豊富であるという性質があります。その特性を生かして、様々な最終製品を製造することが可能です。さらに、生物由来の素材は、合成ポリエステルなどに比べて繊維が多孔質であるため、着色剤がより簡単に結合できるというメリットもあります。バイオセルソルは、酵素を使って木材パルプの溶解性を向上させる技術です。
And this enzymatic treatment improves its ability to dissolve in alkaline solutions.
スピノバ社はセルロース繊維を作るにあたり、他社と全く異なる方法をとっています。具体的には、木材パルプから直接テキスタイル用繊維を作り出し、水の使用量を綿花栽培での生産と比較して 99% 削減することに成功しました。
The process is the core of our technology because we don't dissolve the materials, we only grind them mechanically. We in a way open the structure of the cellulosic fiber so that the surface area of the fibers increases. and then a lot of hydrogen bonding can be formed in the drying of the materials.
2015年に設立されたスピノバ社は、50人程度の従業員を雇用するまで成長しています。
Today we are working in our second generation pilot facility in Jyväskylä. We can produce some tens of thousands of kilograms fibers annually, and we aim to scale up the production to first industrial scale mill by the end of 2022.
さらにスピノバ社は主要な消費者ブランドと提携して自社の繊維を商品化しています。
Some of our cooperations are already public and some are still confidential. At the moment we are working together with about 10 brands and we have published a cooperation with the Norwegian Bergans, a sportswear brand, and Finnish Marimekko, a fashion brand, classic fashion brand from Finland, and also with the Danish bestseller that covers several brands.
日本は近代より新しい素材の開発に取り組み、世界の繊維産業を牽引してきたという歴史があります。本日、その繊維開発の未来を担う日本の専門家の皆様のお話を伺えることを大変光栄に思っております。最初にお迎えいたしますのは、日本化学繊維協会専任副会長並びに日本繊維産業連盟事務総長の富吉健一先生です。富吉先生はメキシコ日本大使館一等書記官、経済産業省局長、日本貿易振興会ジャカルタ所長などを歴任された後、2019年4月より現職にてご活躍です。川上から川下までの繊維を含むプロセス、貿易、産業、イノベーション、そしてサステイナビリティまでの幅広い知見をお持ちでいらっしゃいます。
Good morning, everyone. I'm Kenji Tomiyoshi, Executive Vice President of Japan Chemical Fiber Association. Today, I'm really glad and honored that I can give all participants a speech about the Japanese chemical fiber industry. Today's topic is about chemical fiber industry supporting the realization of sustainable society. Before talking about sustainability issues, I will briefly explain the global fiber demand. The world demand for fibers is likely to expand mainly around emerging market. However, it is difficult to increase the production of natural fibers like cotton because of limitation of farmland, which competes with food production. Chemical fibers would be the only choice to support the increasing demand. As chemical fibers have various outstanding functions, for example, strength but lightness, depending on the fiber design. Not only do chemical fibers make our lives rich, providing comfort, design, and durability in clothing, but also chemical fibers are essential to our lives even in non-clothing applications, such as medical care, construction, automobiles, and aerospace. Besides, chemical fibers contribute to the realization for the sustainable society, resolving global challenges through the functions and performance like reducing weight of aircraft and purifying water and air. On the other hand, there are negative influences of chemical fiber industry on the global sustainability, such as dependence of fossil resources, textile waste, marine pollution, and environmental pollution in the manufacturing process, which are really important issues. Next, let's turn to our chemical fiber industry's efforts for realizing a sustainable society and the challenges. In order to realize a sustainable society, it is an urgent challenge for the chemical fiber industry to shift to the resource circulation model for achieving the goals of Paris Agreement and the United Nations Sustainable Development Goals, SDGs. This slide shows the chemical fiber industry's two kinds of challenges concerning the sustainability. The first challenge is making a circulation system. As you can see the blue area in the slide, there are mainly three issues: PET recycling, fiber-to-fiber recycling, and use of bio-based raw materials. From the point of view of decarbonization and the effective use of resources, while used PET bottle recycling for polyester fiber is put into practical in the short term, we think we should shift the chemical fibers raw materials to renewable materials, which don't emit CO2 in their life cycle in the long term. The second challenge is for reducing environmental burdens, which are highlighted in orange in the slide. There are mainly three challenges: reduction of CO2 emission, chemical substance management, and response to the problem of marine plastic pollution, fiber fragments. I will explain briefly about one topic of each type of challenge. First, I will talk about the common challenge for realizing the circulation system, highlighted in the blue on the previous slide, which is introduction of certification systems. In order to spread environmentally friendly products, we think it is important that consumers become aware of the value of products using recycled or bio-based materials. To do so, it is necessary to establish the system for labeling or certification products so that end-used industries and consumers can evaluate the environmental impact of the products and make the correct choice. In particular, as for fiber-to-fiber recycling and chemical fibers using bio-based raw materials, further technological development are needed, and governmental support is desirable. Next, I would like to explain about the problem of marine plastic pollution as a special topic of another challenge to reduce environmental burdens. According to EU's survey, textiles are the third largest source of microplastic causing marine pollution. And the Osaka Blue Ocean Vision agreed in 2019 at the G20 Osaka Summit sets a goal of reducing additional ocean microplastic pollution to zero by 2050. Under these circumstances, we should seriously address the problem of fiber fragments coming from textile products to resolve the microplastic problem in the marine. In order to implement the proper and effective measures, we think it is important to obtain scientific knowledge of the amount and distribution in the ocean, the originating sources, the runoff routes, and the impact on the ecosystem. The first step is thought to be standardization of a test method to obtain the exact data. We, Japan Fiber Chemical Association, are promoting standardization, the test method for measuring the mass of fiber debris emitted from a domestic washing machine as ISO standards. Considering the present situation based on the objective scientific grounds, we think we must tackle the problem of marine plastic pollution cooperating with related industries such as washing machine, detergent, apparel or textile manufacturing industries, and also sewage disposal industry. We, Japan Chemical Fiber Industry, aim for the industry where sustainability and development are harmony. Thank you very much for attention.
富吉先生ありがとうございました。次にご登場いただくのは、国立大学法人信州大学繊維学部の村上康教授です。村上先生は産学官連携のリーダーをされ、日本の大手繊維系企業などの連携で優れた研究開発プロジェクトの実績がございます。国内では最新のグリーンテクノロジーの開発並びに、最先端リサイクルシステム競争で産学連携をリードされています。今後のフィンセレスの RDI 研究開発イノベーションにおいて、日本側の重要なメンバーとしてご協力いただく予定です。
I'm Jussi Murakami, Industry Academia Collaboration Officer. Thank you for giving me the opportunity to talk. Today, I will talk about future direction of recycling system of cellulose-based fiber. I will introduce key technologies of cotton recycle and our collaborators in Japan, including the futures. Shinshu University is a Japanese national university in Nagano Prefecture, Japan. Shinshu is the old name of Nagano Prefecture. Winter Olympics was held at Nagano in 1998. Area of Nagano Prefecture is 13,560 square kilometers. It is 40% of Finland area. Forest area is 10,600 square kilometers in Nagano Prefecture. 78% of total area of Nagano Prefecture is covered in forest. We are working on research on cotton recycle. Recycling method is determined by fiber length. When the fiber length is longer than 2 centimeters, we can get spinning cotton. When the fiber length is shorter than 2 centimeters, we can cotton paper. We think about how to make a cotton paper. And when the fiber length is shorter than 3 millimeters, we can get cotton powder. We think about how to make a recycling of cotton powder. I will talk about key technology of cotton to paper. I introduced dry fiber technology, which is developed by Seiko Epson, Nagano Prefecture Company. Recycling paper from printed documents through the fibrillation, binding, and foaming without water. Now we are doing joint research. Today, Mr. Ichikawa, the development manager and executive officer of Seiko Epson, is invited. Next key technology of chemical recycling from cotton powder is rayon process. Now, Diabo Rayon is only company of the viscose rayon in Japan. They are interested in an alternative process to viscose and applications of recycling cotton. In Shinshu University, Professor Goto and Kimura study the cellulose regeneration process using ionic liquids. We are doing joint research. Today, Mr. Fukushima, CEO of Diabo Rayon, is invited. Another key technology of biorecycling from cotton powder is biodegradation of cellulose and plant factory to cotton. Our faculty has Department of Applied Biology and the Shinshu University Plant Factory, SU Praf. This photo shows the plant factory using a container. The building behind the container is SU Plaf. I will introduce our future collaborator. First key technology is recycling cellulose acetate and diesel. Diesel is one of the leading cellulose company in Japan. Today, Mr. Shiwaku, Senior Managing Executive Officer, is invited. Next key technology is recycling used disposable diaper Unicharm. Their ozone treatment has an advantage over the conventional method, such as high pressure steam treatment or wash separate treatment. Today, Dr. Miyazawa, the development leader of the method, is invited. Thank you for your attention.
村上先生ありがとうございました。続きまして、国立大学法人信州大学繊維学部梶原寛治リサーチフェローにご登場いただきます。梶原先生は高分子化学の専門家として様々なプロジェクトに取り組まれていらっしゃいます。最近では H&M の非営利団体である H&M ファウンデーションと香港繊維アパレル研究開発センターのプロジェクトにおいて混紡素材のリサイクルシステムの開発に貢献されています。梶原先生は国内外との豊富なコラボレーションのご経験があり、日本とフィンランドの連携においても積極的にご賛同いただいております。
The intention of my talk is to draw your attention to the traditional way of life, which was necessarily sustainable. I would like to demonstrate that the social, economic, technological, and logistic restrictions in Edo, ex-Tokyo, did not prevent people from enjoying their fashion and life, but promoted sustainability. In the pre-industrial era, the life was slow and inefficient. Edo period. The pre-industrial era lasted from about 260 years from 1603 till 1868. At those days, Japan closed the country and prohibited the direct contact with foreign countries. It was also difficult for ordinary people to travel freely. In consequence, Edo had to be self-sustained. In the present time of the industrial era, the first priority is efficiency in all aspects. The technology has been developed accordingly. The supply chain is constituted of linearly connected components, resulting in huge waste, like blood clots. How can we technology provide efficient vein for blood to circulate smoothly in the post-industrial era? In the industrial era, the supply chain is highly sophisticated for the efficient production and distribution of the product to consumers. But the components in the supply chain are not necessarily interlinked. The involved technology to improve the efficiency was developed independently in each component. Knowledge and data management would become crucial for promoting interactions among all sectors of industries and consumers in the post-industrial era. The supply chain should be looped and its components become interactive. Is there anything we should learn from our past? Let's look back the pre-industrial era, that is, the Edo period in Japan. Edo, ex-Tokyo, was a self-sustained city. Main energy sources were wood and charcoal. The ashes were collected and supplied to dyeing and other industries. Human waste, feces and urine, were collected and fed to vegetable farmlands in the suburban of Edo. 90% clothes were second hands and used till fallen in pieces while repairing parts to parts. Over 1,000 recycling repairing businesses were active in town. Local production was made for local consumption. Edo was built on marshy area faced to the sea, and its population was over 1 million in 80,000s. Yet all the vegetables and fishes were supplied from the suburban area and the bay. People wasted nothing. Even feces and urine were collected and sent to the farmland composted. Most of ordinary people in Edo bought second-hand clothes. There were many second-hand clothing stores along the riverbank. Over 1,000 small recycling and repairing businesses were active in town. Edo was a sustainable city, but it was a pre-industrial time when only renewable resources and human power with handmade tools were available. The life was flowing slowly, and people were much closer to the nature. The rapid industrialization has brought high efficiency in manufacturing, but we lost resilience in terms of the coexistence with the nature. Sustainable society of Edo was supported by local production for local consumption. Product design for reuse and recycle is important, as represented by kimono. No waste. Town waste were back to the farmland and surrounding woods. There were various small businesses for collecting and recycling town waste. Looped supply chain, artery and vein should be reconstructed by creating new businesses for resourcing waste. We cannot lose efficiency, but I would like to recover our resistance as a member of the nature. A small step will be to utilize the technologies so far developed and reconstruct the series of technologies for a comprehensive system of artery, vein, and supply chain for smooth blood circulation. Let's see the actions for sustainable textile loop. For example, the parts of garments could be reused by patching pieces together. G2G recycling system is operating in Hong Kong and Stockholm. Most of the fabrics for garments are composed of various sources of fibers, but cotton and polyester share over 80% of fabric resources. Our priority is thus given to recycle cotton and polyester blends. No efficient fiber-to-fiber recycling process is available at present. A hydrothermal process is capable of separating cotton PET blends and recovering PET fiber without deterioration. A chemical system is capable of separating cotton PET by decomposing PET into DMT and recovering cotton. DMT is polymerized to PET. The hydrothermal system was developed as a Hong Kong RITA project, supported by the H&M Foundation. The chemical system is supplemental to the hydrothermal system for multiple recycling. Here we gave a priority to material recycling or recovered PET or cotton. The characteristics of two recycling systems are summarized in this slide. Unfortunately, you have to sacrifice one of two components of blends fabrics for material recycling. By combining two systems, we can construct a system for multiple recycling. This slide shows a PET recycling loop. This slide shows cotton loop. A new system is thus constituted of two recycling systems joined at garment. Two circles form now an infinity circle. The inner circles denote the hydrothermal processing and the outer circle the chemical processing. A long journey for sustainable society has begun with a small step as a new textile loop from the cradle to the grave and back to the cradle. Thank you for your attention.
先生ありがとうございました。最後に株式会社クラレ繊維カンパニー星野秀樹理事にご登場いただきます。星野様は10年以上にわたり同社のクラレヨーロッパに赴任されたご経験をお持ちです。本日はそのようなご経験を交えながらバイオマテル開発に関する企業の見解および提携のアイデアについてお話しいただきます。
Hello, my name is Hideki Hoshiro. I'm the director of Kurare Fiber and Textile Division and the specially appointed professor of Shinshu University. Firstly, I would like to mention Kurare is only one Japanese partner with VTT, and we already joined some VTT project. Kurare was established on 1926. The capital is 740 million euro, and the net sales is about 4.7 billion euro. The main products are vinyl acetate related business, isoprene business, fiber and textile, and functional material business. Today, I do not have much time to introduce Kurare's all activity, so I hope you will check the Kurare homepage. I will explain fiber and the textile business briefly. Kuralon and Kuralon K2 is 100% polyvinyl alcohol fiber. The polyester fiber for textile use, Kuralino, is artificial leather. Vectran is super high strength and heat resistance fiber. Magic tape is hook and loop fastening. And Kuraflex is spun-lace non-woven fabrics. Kurare is world's biggest PVA resin and fiber producer. The biggest application is polarized film for liquid crystal display and water-soluble wrapping film for the soap of washing machine to P&G. The polyvinyl alcohol is biodegradable by microorganisms in the presence of water and oxygen. So polyvinyl alcohol is aqueous solution is categorized as an inherently biodegradable material. Exaval is chemically modified PVA. The resin is water soluble and hot melt and biodegradable. Kuralon is globally #1 brand PVA fiber. Depending on the molecular weight, chemical structure, and spinning process, we can produce water soluble type and non-water soluble type. This binder fiber is famous for paper making. During a dry process, PVA fiber dissolve and perform excellent internal bond. There is a water-soluble staple fiber. We can adjust the dissolving temperature from 20 centigrade up to boiling temperature. The current application are embroidery backing, superfine count cotton, and wool yarn. After mixing with cotton and wool and water-soluble staple fiber, we can make spun yarn very easily. During washing of fabric, PVA fiber dissolve, and we can make the spun yarn. This is a water-soluble sewing thread. During the recycling, the operation to taking the bottom is still manual and very hard work. Water-soluble sewing thread solve this problem. Here is just idea for the collaboration between Finland, Kurare, and Shinshu University. #1, high-strength cellulose fiber. My idea is a copolymerization between cellulose and biodegradable polymer as cross-linker. and making a high molecular weight polymer. And by using the wet spinning method, we can make high tenacity fiber. Number 2 is lignin fiber. By mixing a high content of lignin and small content of PBA resin and water and dry spinning process. Number 3 is plastic mold alternative by cellulose. Air-laid nonwoven by cellulose fiber, biodegradable hot melt PBA fiber, and hot pressed. Number 4 is effective utilization for recycled fiber and waste animal hair. The problem for recycle from fabric to original staple fiber by carding is the damage of the fiber. The fiber strength is going down, fiber lengths, it becomes shorter and shorter. Then very difficult to make spun yarn. When we mix the water-soluble fiber to recycled fiber, it's very easy to make spun yarn and fabric. During washing the recycled fabric, PBA fiber dissolved to the water and get 100% recycled textile. Same concept for animal hair. We discard and burn the much animal hair worldwide. For example, the camel hair is very warm and good animal hair. However, people do not use this. Short and coarser wool also. We want to reduce the discard animal hair. Number 5, recycled system by water-soluble sewing thread. As I already explained it, this PowerPoint, so I will skip this idea. Number 6 is wood fastening. Kurare is the biggest hook and loop fastening producer in Japan. When we mix lignin or wood powder with PBA hot melt resin, then we will be able to produce wood fastening by injection molding. From here, some topics from sustainable R&D and business in Japan. Professor Dr. Ajiri for Tohoku University developed cerium dioxide nanocatalyst. He succeeded to make hydrogen gas and phenolic compound at about 300 to 400 centigrade. Torre modified the cellulose to cellulose ester. This shows thermoplasticity and suitable for melt spinning. The brand name of this fiber is Ponsse. The problem for recycle is to sort many kinds of material like polyester, nylon, polypropylene, and cotton, and very difficult to classify them. Professor Dr. Kimura found out the new recycle system, not the material, but the color. After classified each color, he mixed polypropylene and made the sheet for consumer product. 20% of water consumption for all industry is for dyeing. So we use much water for dyeing process. Shortage of water is another big issue for SDGs. Professor Dr. Hori of Fukui University is the authority of supercritical dyeing process. Nike, Adidas, and Mizuno are already announced that they do not sell the conventional dye knit fabric, but supercritical dye fabric. Now, polyester is very popular for this dyeing process. Currently, Dr. Hori developed new dyeing stuff for cotton. So we will be able to work together with Finpress for supercritical dyeing rayon or cellulosic fiber like a spinova. So thank you very much for your attention.
星広様ありがとうございました。本日は両国の専門家の皆様より、それぞれのお立場から多方面にわたるお話をお伺いしました。私たちの未来は、革新的で持続可能なソリューションを開発する科学にかかっています。フィンセレス研究コンソーシアム、フィンランド自然資源研究所、そして本日参加しております私たちのチームは、 日本の皆様と共により良い未来のために貢献したいと願っております。